Okay, so the next overview lecture is by Chen, and he'll continue talking about developments in quantum magnetism.
So good morning, everyone. So my name is Chen. I'm from Fudan University of China. So I'll talk about some recent development in quantum magnetism following the tutorial lecture by Ying-Jer. So this talk, this tutorial is very simple. So there is no field theory, no exotic phenomena, no fractionalization, no topological order, no hard things in this tutorial. So there are two parts. Let's see how far we can go. So I begin with the part one, which is a description of, which is the introduction of topological magnons, particularly focus on the case of Y magnons. Actually, can people hear me in the back? Okay, good. So the second part will be some thought of detecting hidden multipolar orders in quantum magnetism. So let me begin with part one, which is topological magnons. So what is particularly for the case of Y magnons? So in the beginning, I will explain what is a Y semimetal. So over last decades, about 1 decade, maybe 9 years old. So there are lots of activities in the field of Y semimetal following the discovery of topological insulator in 2009, 2008. So Y semimetal, I don't think it was first proposed in this paper. It was proposed earlier than this paper, but the excitement was made by through this paper. So in this paper, they proposed the non-trivial bulk surface correspondence and point out the existence of Fermi-Arc surface states for the topological semimetals. So let's see what's the history like. So what is a Y semimetal? Y semimetal is a particular Banner structure in a three-dimensional bulk material. It's a free electron property. It's just in a three-dimensional system material, the electron hopping on the lattice and form some kind of bands, block wave function. They have some bands. So it turns out that sometimes the Fermi surface, the Fermi surface composed of a few discrete momentum points rather than a surface. It's just the points. So the bands, the conduction band and valence band touch at a point. So these points are called Y points. So this Y points is not along some particular, not at some particular high symmetrical momenta. It's some arbitrary momenta. And these degenerate points always appear in pairs. And if you linearize the equation, so let's see if there is any. Yeah, so there is an example of this. So this is the band structure, Kx, Ky, and energy, and the conduction band and the valence band has a band touching at some particular point in the momentum space. This point is actually called a Y point, and if you linearize this equation, linearize the dispersion or linearize the Hamiltonian at this point, you obtain so-called K dot P theory. It's a simple Taylor expansion type of calculation. It's described by this sigma is a Pauli matrix because there are two bands involved. It's a simple 2x2 matrix with some, this is velocity, this is momentum, and this identity matrix. So these Y points always come in pairs because of so-called Fermi double theorem. So there are these Y points. These points is categorized by the chirality and the so-called type. So the chirality is either plus or minus 1. So they always come in pairs. So with different chiralities. So yeah. So the Y semimetal was first proposed in the so magnetic Y semimetal was first proposed in the context of Pyrochlore iridates. So this is the example of Pyrochlore iridates, iridium atoms from a lattice called the Pyrochlore lattice, and Shannon Wang and his collaborator studied some extended Hubble model on this lattice and studied the impact of magnetism on the conducting band structure property of the conducting electrons. So this material has a huge material family, and if you change the change certain atom, sub-atom, so there is a change of this magnetic property. So almost all of these materials experience a metal insulated transition with the emergence of magnetism. So Shannon first carefully studied the effect of magnetism on the band structure property of the electrons. So this is his first diagram. He changed this for the U. This parameter categorizes the effect of correlations. So if you introduce a strong correlation, that will enhance a strong correlation and induce magnetism. And he found that in an intermediate correlation regime, there is a new phase which is called the Dirac semimetal. So in his paper, he labeled this as Dirac semimetal. Rather, it's an example of Weyl semimetal. So the system has some magnetism. So when magnetism enters, so the electron moving on the lattice will feel this magnetism. So the band structure of the electron is being modified and reconstructed. And turns out in the band structure, there is a non-trivial band touching at some point, and this point is called Y points, as I have explained. And this is the band structure. In the beginning, without magnetism, there is a huge band gap. It's an insulator, and you turn the correlations, induce the band gap. You close the gap and form this semimetal-like dispersion. So he found in his paper in the three-dimensional Brillouin zone there are 24 Y points, so 12 pairs. Each one direction contains 3 Y points, and there are 12 pairs. So he plotted this band structure along high symmetrical momentas for a slab of material. So this material, this geometry is in one dimension it's finite, and in the other 2 dimensions is infinite. He found that there is a non-trivial surface arc connecting these projection of Y nodes. So these points are Y nodes. The projection of the Y nodes onto the 2-dimensional two-dimensional Brillouin zone of this 2-dimensional slab of materials. So there is a non-trivial arc, surface arc connecting these projections of Y nodes. Yeah. So this is the calculated result of surface spark correspondence in this particular materials. Yeah. I forgot to mention, but red blue means these Y nodes have different chirality. One is +1, the other is -1. So the meaning of chirality is associated with some kind of Chen number, which I will explain now. So why there is a non-trivial surface spark correspondence? Why there is a non-trivial forming arc connecting the projection of Y nodes with different chirality? So what it comes to the definition or the notion of chirality of Y nodes. Suppose this is the Y nodes. So this is Kx, Ky, and energy. There is a linear band touching at some point in the K space. So this is linearly dispersive. Now you choose a circle, or you choose a cylinder. You fix one radius of you fix the momentum along a radial direction, and then you choose this cylinder. So this cylinder, if you expand this cylinder, defold this cylinder, unfold this cylinder, this becomes effectively a 2-dimensional system because you have fixed one momentum, right? For the remaining 2 momenta and energy, it's a effective 2-dimensional system. Because this cylinder does not cross with this band touching point, this effective 2-dimensional system is a gapped system. For any gapped 2-dimensional system, you can define a Chen number. You can define Chen number for this effective 2-dimensional system. It turns out the the conduction band and valence band have a opposite Chen number. One is +1, the other is -1. So for instance, if the valence band has a Chen number equal to -1, so equal to 1, so that will be a forming point, or that will be an edge state corresponding to this effective two-dimensional system, right? So now imagine you move this cylinder, you change the size of this cylinder from small to big. So for each of these radius, each of this value of this radius of the momentum, there will be a surface state. So as you change this radius, eventually you will cause this radius, this cylinder will cause another y point, and then that will correspond to the termination of a forming arc. So that's the reason why there is a forming arc and a forming arc connecting the two y points. So that's the chirality of these y points just corresponding to the Chen number of this effectively two-dimensional band. Yeah. So is that clear? So this is a simple-minded explanation why there is a forming arc, why there is a non-trivial surface bulk correspondence. There is in this paper they actually using so-called using the original mathematical definition of barrier connection to define this define the source of single multiples of this barrier of the y point. So this is the basic concept of this Weyl metal and the basic property of Weyl metal. So it was originally proposed in the context of in the context of Pyrochlore iridates in the presence of magnetism. But the magnetic Weyl metal is very hard to find in nature. This requires strong correlations, and you should keep the correlation to be such that it is located in this particular intermediate range, such that the system can develop a Weyl metal. So it's relatively difficult to find in nature, and so the real Weyl metal in nature was discovered in the context of titanium arsenide, which is not a magnetic Weyl metal. It's a Weyl metal that breaks inversion symmetry. So it's a non-central symmetrical material. So to obtain Weyl metal, one have to either break time remote symmetry or break inversion symmetry. So magnetic Weyl metal is an example that you break time remote symmetry. So this example is a Weyl metal that break inversion symmetry. It was discovered by a Princeton group and the AOP group in Beijing in this families of materials. They found both the bulk band touching and the surface forming arc connecting the projection of the Y nodes. So that was a great discovery about 3 years ago. So that's the later on. That's a lot of extension of these topological semimetals, including type 2 Weyl metal, hybrid Weyl metal, Dirac semimetal, nodal line semimetal, even our gas fermion semimetal, and some even nodal line new fermions proposed by a Bovenick group. So that's all these examples of topological semimetal in the context of electron system. So now we want to turn attention to magnetic system, to spin system, whether one can have these topological excitation in the system of motor insulator. So now I switch to magnetism. So this is the tutorial lecture. So let me begin with antiferromagnets. So historically, ferromagnetism was discovered more than 2,000 years ago by Chinese, by Indians, by Greeks. So they found the ferromagnetism because ferromagnetism have a permanent magnetic moment. You can easily see by just attach this magnet to some iron, to steels. Then there is attractive interaction between these permanent ferromagnets with other steel, other materials. So antiferromagnetism was very actually much more common than ferromagnets, but it was not discovered until 1950s, 1949, 1950s. after the invention of neutron scattering, where people can see these non-trivial propagating wave vectors of this magnetism. So they see a magnetic Bragg peak emerge. They found a different non-trivial magnetic propagating wave vectors in the Bragg scattering of a neutron scattering measurement. So now this is the example of anti-magnetic Néel state for a square that is Heisenberg model, and this is example of so-called 120-degree state for the triangle that is Heisenberg model. So now we know most known magnets, actually the majority magnets are antiferromagnetic rather than ferromagnetic. So once the system develops a magnetism, so develop some kind of magnetic order, we can, to categorize the magnetic order, so besides this static structure of this magnetism, there is also so-called magnetic excitation associated with this particular magnetic order. So as pointed out by Ying-Jer, if you consider the fluctuation of these magnetic moment, so this is the particular direction of some spin component on the lattice. Now you consider the coherent propagation, a collective organization, a collective fluctuation of these spin moment on the lattice. It forms some kind of wave, and this wave is called a spin wave. There is a very simple mathematical transformation, called the Holstein-Primakoff transformation, to reparameterize the spin vector in terms of spin operator in terms of some hardcore boson language, and then you can mathematically compute the excitation spectrum associated with this magnetic state. So to categorize a phase, to categorize the magnetic property, besides the static structure of magnetism, besides the particular arrangement of the spins, particular arrangement of the local moments, we also need to understand the excitation, the fluctuation, the excitation of this corresponding to this underlying structure of the magnetic order. So that's why we need to understand the spin wave excitation of this antiferromagnetic state. So this is the example of spin wave excitation in order the antiferromagnet, which is a material ytterbium tennate, is a particle magnet. So this is the theoretically calculated spin wave dispersion along certain high symmetrical momentum points, and this is the neutron that's a neutron scattering measurement. So neutron carry spin. When neutron enters, neutron creates a spin flip and excites the spin wave excitation in the magnetic order the materials, and they detect this energy momentum loss of the neutrons, and you can see a well-defined dispersion. And this is the comparison between theory and between theory and experiment. So spin wave, this Holstein-Primakoff type of spin wave theory provide a very nice, calculation or explanation of a magnetic excitation in a conventionally ordered magnet. So this is this is simple, but a very useful way of understanding excitation or basic magnetic properties of ordered antiferromagnet. So this is the basic introduction of the physical property of antiferromagnet and how to measure the spin wave, how to compute the spin wave excitations of a magnetic system. Now we turn to this the main topic of topological magnons. So the important message I want to deliver in the first part of the talk is that this is topological band structure of electrons, topological insulator, Weyl semimetal, Dirac semimetal. These are band structure topological property. It's the topological property of the bands. So once you said that, once you realize that, so this topological property is independent from the particle statistics. It's independent of the statistics of particles. that reside on the lattice, reside on the band. So that means, so this wire band touching, this Dirac band touching, these topological band structures of electrons, can be also realized. At least some of them can be realized in the excitation spectrum of a magnetic ordered system. For instance, can be applied to it can be applied to photons, can be applied to magnons, to phonons, etc. So, say it again. Yeah, question. Yeah. Yeah, that's a good question. Yeah, so I'll come back to that. So there are differences, right? So there are differences, but the point is it's a band structure property. So I haven't talked about the filling of these, how the particles are filling these bands. So I'm just talking about the band structure property. You not think about taking any kind of particles, putting on the band. Just think about the band itself. So these bands, this wire band touching, as I said, these are topological property of the band. It's independent from the statistical particles. So it can apply to other bosonic systems, such as photons, and magnons. So in this talk, I'm focused on the magnons, which is the magnetic excitation of all the antiferromagnet. Yeah. So I start with an example, a physical example, how to to illustrate the idea. I introduce this example. Yeah. So to illustrate the idea, I use this example of a Breezen-Parker magnet. So this is the structure of the Breezen-Parker. It's a material which is lithium, indium, chromium oxide. So the chromium, which is chromium ion, is magnetic. So the chromium ions form a Breezen-Parker. So this is different from conventional Parker, where this blue and red tetrahedral are equivalent under inversion symmetry. So each lattice side is the inversion center, and this are related by inversion symmetry. But for Breezen-Parker, it's not. This is not no longer an inversion center. So this tetrahedral are not equivalent under inversion. So there's no inversion symmetry here. So as a result, these are not equivalent. The interaction on these on a bond on this tetrahedral are different from the interaction on this bond. So one can write down some minimum model, just considering Heisenberg exchange on this tetrahedral and this tetrahedral. They have different exchange couplings. One is J, the other is J prime. And in addition, there is a single ion anisotropy. Ying-Jer was talking about single ion anisotropy for this high spin local moment when spin orbit coupling is important. For this chromium, it got the total spin 3½ which is fairly large, and we need to worry about this single ion anisotropy. And it turns out that the single ion anisotropy is either favorable in plane, or single easy axis anisotropy. So this Z is the local Z. It points into the center of the tetrahedral. So this, so Ying-Jer also mentioned this for tetrahedral. So this is the local Z direction. It's defined on a lattice, on a global cubic lattice. This local Z is a global 1-1-1 direction. The 1-1-1, 1 bar, 1 bar, 1. These kind of 4 directions. So depending on sign of D, if D is negative, it's an easy axis anisotropy. Favor the spin to be aligned with the local Z. If D is positive, favor spin to be perpendicular to the Z. So that's for the easy plane anisotropy. It turns out that you can do some simple algebra. You can, because this exchange is defined on a tetrahedral, you can glue them together. And this is the upper tetrahedral. you can group them as the total spin on a tetrahedral, and for the down one is the total spin on the down tetrahedral. If the exchange interaction is antiferromagnetic, so if you treat the spin classically, because the spin is rather large, the spin 3½ is legitimate. It's legitimate to first treat the spin as a classical vector to understand the classical ground state in the beginning. So this will simply favor the total spin on tetrahedral to be 0, both the upper one and the down one. So that's the condition to optimize the exchange part of the energy. But for the single anisotropy, if the D is positive, then we prefer the spin to be parallel to the Z direction. So either parallel, this is perpendicular. D is less than 0. We favor spin to be. It turns out for either case of the sign of D's, for either sign of this single anisotropy, so this condition can be optimized. No, this condition and this condition can both be optimized. So one can obtain the four-phase diagram, for different values of J prime over J and the single ion anisotropy. Yeah, we only choose positive ones. For the negative one, which is this one, it's a unique ground state. So this unique ground state is basically all in or out. So if sum of the spin together is equal to 0, the trivial state. But for the sign to be positive, so there is actually a degeneracy. Because if ever the spin to be normal to this Z direction, the spin to be oriented in the plane normal to this Z direction. So you can obtain this four-phase diagram, and these region 1 and region 2 have the actually they are so they have corresponding different magnetic structures, and region 3 is another magnetic order. So region 1 and region 2 have I think this is probably some typo. I think region 1 and 2 is this magnetic order. Region 3 is this magnetic order. There is a typo here. This is 3. This is 1 and 2. Yeah. So region 1 and region 2 have the same order, but they belong to the same phase. But there is a dashed line to separate them. So these two have the same magnetic order. They are same phase. They have the same type of symmetry breaking pattern, but they are distinct in a sense. They have distinct topological properties of the excitation. So their excitation have distinct topological properties, but they are the same phase. Remember, so they are distinct at the excitation spectrum level, but the ground state magnetic order is identical. So they are the same phase. The symmetry breaking pattern is the same. So if you go from 1 to 2, there is no free energy singularity. So they belong to the same phase. It's not a phase transition, it's a crossover. So it's a crossover of the excitation spectrum of the topological property of the excitation spectrum. So how do we see it? So this is the so-called quantum order by disorder effect. Because the spin to be aligned in the normal to the Z direction, it turns out so the system can satisfy this condition and this condition at the same time, but there is a residual degeneracy. The spin can orient in the XY plane, in this XY plane, local XY plane, by arbitrary angles. And if you parameterize the ground state with some angles, there is a degeneracy. And this degeneracy is not, this is emergent U1 degeneracy, which is absent in the Hamiltonian. So the Hamiltonian has a very low symmetry. It only has lattice symmetry and time roll symmetry. So the ground state manifold, the classical magnetic order manifold, has a emergent U1 degeneracy. So this U1 degeneracy is not going to be protected by the Hamiltonian. So thermal fluctuations or quantum fluctuation will lift this degeneracy. Here, if you consider quantum fluctuations is which is quantum zero-point motion of this spin wave mode, will lift the degeneracy. So I don't want to get into details. So this quantum zero-point motion will select some particular magnetic order in these regions, and once it's selected, we favor some unique, some discrete type of magnetic order. And you find that this magnetic order, you carry out this spin wave kind of calculation, which I have just explained earlier. Use the Holstein-Primakoff bosons to compute the excitation spectrum. And you can find that this system has a non-trivial band touching. From gamma to X, there is a non-trivial band touching in the excitation spectrum. So this is the magnon mode, this is the spin wave mode, and there is a band touching. This band touching is a wire band touching. This is wire band touching. So these are wire points, and you can find all these wire points in the Brillouin zone, in the three-dimensional Brillouin zone. They come in pairs. So different color means different chirality. So as you mentioned, as you asked about this, there is the difference between fermion and bosons. Fermion, there is a Fermi level. You can add the particles into the system such that your Fermi level is right at the y point, right? So then your Fermi surface is just points. But for the bosonic system, especially for these magnons, these are bosons. These are bosons. So boson, there's no such a thing called the Fermi surface of bosons. So there is no surface. If you have finite number of density of bosons hopping on a free band structure of these magnons, they will condense. They are unstable, right? So this band touching can only appear at finite energy, at the excitation spectrum. It's not you cannot feel the states up to this level. They are all at the excited level. So this is the excitation spectrum of these bosonic particles. They're not, this is not being occupied. Only if you want to occupy, you can use thermal excitation. You can thermally populate these bands by introducing temperature. Yeah. No. So Holstein-Primakoff boson, you just consider some magnetic order and consider fluctuation, consider excitation with respect to these magnetic order you find in the spectrum. So you can occupy this band by thermal fluctuation. If you define a temperature, you can populate these bands, with these bosons, with energy, with entropy. So these are your question. Oh yeah, so one of them, so region 1, so this is the magnetic order for region 1 and 2. This is 3. There is a typo in the plot. So region 1 has this non-trivial band touching, but the region 2 does not. They are distinct topologically in the spectrum, but they are same state. They are in the same phase. If you go from one to the other, there is no free energy singularity at all. They are in the same phase. They're smoothly connected, but the difference appears in the excitation spectrum. But the excitation spectrum does not. The topological property of the excitation spectrum does not categorize the fundamental property of the phase. They have a gap. Yeah. So as you go from 1 to 2, so these these wire points, they move gradually together and then annihilate and gap out. So as I said, these wire points are protected by is topological protected. It's robust. It's robust. They cannot disappear or created by itself. It must come in pairs. And when they analyze, they also have to analyze in pairs. So opposite chirality, while points with different chiralities must come together, meet each other, then they disappear. So that's why this region 1 with Weyl magnon excitations cover a wider range of phase space because they are robust. Once it's created, it's not going to be one point in the parameter space. It's going to occupy a large region of your phase space. So that's why it covers a large range of your parameter space. Yeah. Yeah. So this is the plot of this surface states. For dispersion, there is a surface arc, and this arc connecting these arc states connecting the projection of these wires with different chiralities. So similar property of this wire electron applies to here, applies to the wire magnon, except this wire magnon must appear at final energy. So these are excited states, not the states near the Fermi level. There's something unique about these wire magnons. So wire magnons, come excitation of the spin. These are spin are neutral objects. It's charge neutral objects. So spin are charge neutral degree of freedom. So imagine you apply magnetic field into the system. For a wire electron, if you apply magnetic field, so so this is the wire spectrum. Some states over here. Now imagine you apply magnetic field. Magnetic field coupled to the electron in a Lorentz fashion. You have Lorentz coupling. You get orbital coupling of the coupled to the magnetic field. It will convert the wire. It will kill the wire nodes immediately. Will convert the wire electron into chiral lambda levels. So it will become things like this. So there is a chiral lambda level connecting these wire nodes with different chirality. So we'll kill these. We'll convert this wire band touching of the electrons into chiral lambda levels. So this is the effect of the magnetic field onto wire electrons. But for the spin system, if you couple to magnetic field, so the dominant effect is Zeeman coupling. It's not this orbital coupling, not Lorentz coupling. It's Zeeman coupling. So what Zeeman coupling does to the system is that you tilt the magnetic order toward the field direction a little bit, right? Originally the spin are some arrangement of spins. Now you apply field. The field tilt the spin towards this field direction a little bit, right? The consequence is that tilt the excitation spectrum a little bit, right? So you don't kill the magnetic order itself. You just apply small perturbation to the system. So wire nodes, as I said, is a topological object. It's protected topologically. It cannot be removed or killed immediately. So once it is there, right? So you apply field, you tilt the magnetic order a little bit. The consequence you move these wire nodes a little bit in the momentum space. So if you change the field, if you increase the field along this way, so you move these wire nodes around in the K space. Eventually, at some point, when the field is large enough, so these wire nodes will meet each other at some high symmetrical momentum points, and then they annihilate and disappear. So they give you a way to physically engineer, physically tune the position, tune the number of wire nodes with the magnetic field. Yeah, I don't think. I think you can do that. You can figure out the right direction of the magnetic field to kill one pair and keeping the other pair unattached. So There's some idea how to probe the Weyls. Obviously, the best way would be neutron scattering, which directly detect the Weyls. Maybe one can even see the surface arc states. The other effect is Subhro effect. If you turn on the temperature, they will excite some magnons onto the bands. The bands will have non-trivial, barrier curvature. So the Subhro effect can be non-trivial because of the different population of these magnons. You can even also measure optically, doing a pump measurement, see the contribution of the Weyls to the optical conductivity. Right? So that is the difference between Y electrons and Y fermions. So there are a lot of extension of this since the proposal of Y semimetal. So there is since the proposal of Y magnons works by Yuan Li in the audience on the Dirac magnons and the experimental discovery of Dirac magnons. There's another line magnons being proposed by some people I don't remember. And there's a magnetic topological insulator proposed by Schneider, Katasula, try to make an analog with the electron topological insulators. So yeah. Yeah, so topological electron topological is a time reversal, require time reversal symmetry. So the difference between magnetic system and the electron system that if you have a magnetic order, you automatically break time reversal symmetry. So that means it's very hard to define, this topological invariant for the band structure of magnons because time reversal symmetry is broken. So you need to figure out the right, this anti-unit operation on the band structure of these magnons. So these people, they point out that under certain lattice symmetries, at some high symmetrical momentum points, you can have some reduced version of Kramers theorem. Then you can define so-called Z2 topological invariant for a band structure of magnons. So they figure out some kind of particular symmetry realization of this magnetic topological insulator. No. These are just views of terminology. Really, they are not insulators. These are not really the same metal. These are just band touchings at some excited states. Yeah, no insulators. Yeah. Yeah. I should put a quotation mark on that. It's really not. No. Don't take that seriously. This is just saying you can define a similar topological invariant for a magnon spectrum versus these electron topological insulators. Yeah. Yeah, it's a property of the band. It's a property of the band. Yeah, don't talk about the feeling of the band. Yeah. So for this, I just want to convey the message that the band structure topology of magnons can be an interesting thing to look at among these magnetic order systems. So the way I was educated is that all these magnetic orders, when system develop orders, everything is a trivial state, then nothing interesting about it. But in the time of topology, now we can have a new interesting observable to examine to examine among these which originally thought to be trivial magnetic order system. So we can have some other interesting things to look for. So this is part of this research is mostly collaboration with my two of my students, Fei Li and Yaodong Li, who is actually transferred to UC Santa Barbara working with Matthew Fisher. And these are two relevant publications. So I only have like 10 minutes, but I'm not sure if you want to let me to continue to this or not. Yeah. Okay. This is some maybe interesting new direction of not really new direction, some new idea along some not very new direction of quantum magnets. So it's called detecting of hidden orders, hidden multipolar orders. First, let me begin with hidden orders in condensed matter physics. So what is a hidden order? So once you see, people see something we don't understand, observe some structure of something we don't have a name, then we call it a hidden order. The hidden order in corruption, hidden order in odds. Yeah, there's some underlying hidden structure up there. We don't know how to name it. Then we call it a hidden order. So the hidden order was introduced in condensed matter in the study of this compound called uranium, ruthenium, silicon. It's a heavy fermion compound. It's a lattice. It has this lattice. Uranium, ruthenium, and silicon. They are layered. And uranium pretty heavy. Got 5F electrons. Almost localized. It has supported some itinerancy, hybridized with ruthenium electrons. So this is the phase diagram. So the important part is this phase boundary. The phase boundary between a paramagnetic state and ordered state in this green region. So there is the phase transition as you go closer, as you cool the system. So this is the pressure, this is temperature. So at ambient pressure around the 17 Kelvin, there is a phase transition. So this phase transition is indicated by a sharp peak in the heat capacity. And if you integrate the heat capacity versus temperature, you find that there is a huge entropy loss. There is a huge entropy drop across this phase transition. Apparently, the system loses entropy to some ordering state, and they call this state called a hidden order, because the people know, the experimentalists, the people who work on this know the system develops some kind of order, but they do not know what precise order the system developed, right? So the entropic measurement tells that the system really orders. Lots of degrees of freedom are lost, but we don't know what's the nature of the hidden order. So because this order, this underlying order, do not couple to your common experimental measure, common experimental probes, such as neutron scattering, X-ray, or any kinds of spectroscopic measurement, or any kind of measurement of the structures. You do not see any signature of the ordering, but the system do develop some kind of order. Right? There's a huge entropy loss, like 50% of R times log 2 entropy loss. So all the parameter is unknown after decades. So that's the introduction of hidden order in the context of condensed matter. So there's lots of proposals of this nature of the hidden order, but it's not really understood. Most likely, this hidden order is some kind of multipolar order of electrons. So electronic multipolar orders which hybridize with local moments in some complicated way, and conventional probes do not couple to that. I think there's a difference. So for this antiphase magnets, it has some structure, and if you invent this neutron scattering, we see it directly. But this one, this hidden order is hide in some other parts of physical hyperspace, electron wave function in some parts of physical hyperspace, and this part of physical hyperspace do not really couple strongly to the usual experimental probes. Right? This part of hyperspace is not related to the density of electrons, not related to the magnetic ordering of the electrons, so then you cannot see it directly. In some other parts of the physical hyperspace, once it's ordered, it will impact the electron property in some way, in an indirect way, but we don't know the nature of this, which part of the physical hyperspace that is relevant for the development of this order. Yeah, this is also people call it dark matter in condensed matter for public advertisement. So there are some natures of hidden orders, such as multipolar order, electron multipolar order, orbital order. So the most important question is how to probe these hidden orders, how to reveal these hidden orders. Yeah, so in this part, I'll just try to propose a thought, propose an idea how to reveal this hidden order in the context of Weyl's magnets. So these so-called intertwined multipolar orders, how to reveal that in the context of Weyl's magnets. So over the years, there are a lot of activity on this material, which is a Weyl's-based triangle lattice. So the Weyl's terbium from this triangle lattice, which is support the effective spin 1/2. We propose it to be a spin liquid. There are some debates, and but the talk is not about this compound. So the discovery of this compound caused a lot of further activities in the study of triangle lattice magnets. There are lots of families of these materials where all of them support rare ions on a triangle lattice. They have distinct physical property. It can be understood in some more or less unified way. So you can write down some Hamiltonian. I think SungBin will explain how to construct these microscopic interacting Hamiltonian for these rare magnets. Let me just quickly go through the basic ideas. So the idea is rather simple. Just don't worry about these complex things in the slides. So the fundamental ideas of this part is very simple. It's come from the simple quantum mechanics. Consider two operators, a Hermitian operator. A Hermitian operator corresponds to some physical observables. So P and Q, they do not commute. They do not commute. Imagine a Q. Q is the system that is the underlying order corresponding to the underlying order or hidden order. So the Q part, the Q corresponding to a Q operator develop some kind of static ordering structure, and but we don't know how to directly measure the correlation function of Q itself because Q does not couple to your experimental probe. So, but Q develop an order, right? But then, we cannot measure Q directly. It's hard. But we know how to measure P. P is some corresponding to some another physical observable. It's very easy to measure, right? So we can measure P, right? But P do not commute with Q. So what does that? We measure P, but P do not commute with Q. So we apply, we see the Q, the correlation function of P. What P does, P act on Q will create a coherent excitation within the space of Qs, right? You apply P to Q, you flip, you create excitation with Qs, and then you measure the correlation function of P's. You actually detect the dynamic property of Q, right? So you measure this object, but reflect the property of Q. So then this, from measuring that, you reveal the structure of the Q. So this is a very simple idea, but it actually works. Yeah. So say it again. Yeah, it give you. I'm just illustrating the idea. There might be some subtlety, but the underlying qualitative idea is this: if you want to see the structure of Q, you measure a conjugate variable, find the operator that are not commute with this object, orthogonal operators, and then you see the correlation function of that. You indirectly reveal the underlying structure of that. Imagine, yeah. Yeah, this is we can give you some examples. Yeah, so this is some Hamiltonian. We write down for a triangle lattice magnet, which side is some effective spin 1/2. It turns out these effective spin 1/2 are built up with a non-Kramers doublet. So this non-Kramers doublet is very special, such that I'm a little bit running out of time, but let me just quickly go through it. So So in this system, the Z component of the spin is dipolar, is magnetic. The transverse component of the spin is non-magnetic. So if you couple the system with magnetic field, the system will couple to Z component of the spin. Likewise, if you do neutron scattering measurement, neutron spin would only see the Z component of the spin, right? So imagine your system develop order in this XY plane, right? In this internal XY plane, in this quadrupolar non-magnetic component, in the XY plane, in the XY component, any kind of magnetic measurement will not see it, right? Because that object is non-magnetic. Right? So you do neutron scattering, do any magnetic measurement, you don't see any signatures, NMR, there's nothing, right? Because yeah. No, there's no U1 symmetry. This is a discrete symmetry. Only that is symmetry here. Yeah, in this context, because of this term here, there's no global U1. There's only discrete symmetries. So you break a discrete lattice symmetry by developing order in the XY plane. Yeah, so if you do heat capacity measure, there is a peak in the phase transition, but you don't know where the ordering is goes, right? You don't know where the system develop magnetic order. So you do elastic measurement like a neutron diffraction, any kind of NMR. You don't see anything. It's hidden. So the way to see it is through this so-called selective measurement. You measure the SZ correlation function. SZ is magnetic. You do neutrons. You see the dynamic properties, but you see the dynamic property of these Qs. Right? So this is the because of time issue. Let me quickly go through it. Yeah. So to detect that these hidden multipolar order when combined elastic and inelastic ones. So these are inelastic ones. So you reveal the underlying dynamic property of this hidden multipolar order in the XY plane. Yeah. So this is the underlying structure of this coherent excitation, just directly tied to the underlying structures of this hidden order. Yeah. So my student actually work out some selection rules on the spectrum. Let me give you a physical example. This is an intertwined multipolar order discovered in this material. So this is the susceptibility measurement for the field in plane and out plane. So for in plane, you don't see any response because the in plane component is non-magnetic. Only outer plane is magnetic. Likewise, if you apply the field in plane and out plane, so for in plane, there's almost no response. For out plane, you get a magnetic response. So in plane component is non-magnetic, out plane is magnetic. Remember this fact. And this is heating capacity, there is a peak around this. There is a phase transition around 1 Kelvin. So if you do elastic measurement, there is a peak at the K point. The system develop order in the K point. So the system develop order, dipolar order at develop SZ order at the K momentum K. The propagating wave vector for the dipolar order is at K point. But if you do inelastic measurement, you are also measuring the SZ correlation function. So then you should see either a flat line or mode, because SZ do not flip SZ itself. But here you see a well-defined dispersion. So this is energy. This is energy. This is the momentum. This is Kx, Ky. You can see evolution of these dispersions. And this is theoretical calculations. The reason you can do that, you can see this well-defined mode is because you have the system has to have order in the hidden XY plane, right? So then you apply SZ, you flip it, you create a coherent excitation. Otherwise, you do not see it. So that's the reason. This is basically this idea. So the system has order in the SX or SY channel, but SX SY channel order is not measurable for any kind of conventional magnetic measurement. But you can measure SZ. SD do not commute with this object. You measure SD correlation function. You measure SD correlator, and this, this apply to that, flip this thing, and then create coherent excitation and record it by neutrons. And this structure of this dispersion directly reflect the underlying ordering of this object. So this is the plot of energy momentum dispersion. And this is the experiment, this is the theory. It has almost perfect agreement between the theory and experiment. Let me just finalize with this part. So the manifestation of hidden multipolar order is rather non-trivial, both in static and dynamic measurement. So this idea is called a non-commutative observables. It can be used to reveal the dynamics of hidden order. Actually, this idea is quite general. Because this observation is general, not just applied to this system. I just use this system, this kind of example to illustrate this idea. There can be non-trivial verifiers here, but I don't have time to mention it. Thanks very much for the time. Yeah.
Like in the extract critical exponents and have some guess as to what universality class they're in, or what the symmetry of the order parameter would be, or is it not?
That's a good question. Usually, this critical exponent is hard to extract in a experiment. Here we only have a specific hit. You need to really close to the TC and focus on the narrow regions. For these irregular silicons, it's not that simple, because there are conducting electrons in addition to the order itself. So it's a complicated problem. It's not a pure order parameter issue. It is impacted by the presence of gapless fermions in this system.
Thank you.
So in the non-ordered side, how would the neutrons, the structure factors look like?
In the non-ordered side,
yeah.
In non-order, it's just paramagnons. The system have not developed magnetic order. Yeah.
Okay. So what feature in those plots are special? There's nothing like that.
There's nothing like that.
Okay.
So once you see this kind of things, that means the system has to have some kind of order. It's a well-defined coherent excitations, in the measurement. This must suggest some kind of strong indication of underlying order forming in the system.
Can you infer something about that, or not really? Can you infer something about the hidden order by looking at these plots?
Yeah, so this just as I said, the system has to have order in the XY plane, in addition to the Z component ordering at the K point. There is a transverse component ordering. At the same time, the system develops a Z component ordering. So that's why I call it intertwined order, intertwined multipolar order. So the dipolar component of SZ orders, at the same time, the quadrupolar or multipolar component of SX, SY orders. So that's because these two objects do not commute, and they develop order at the same time, they order at different wave vectors. Yeah. It's the intertwined orders. Yeah.
Talk about we can detect the magnon signals with the help of thermal Hall effect measurement. So as you have plotted that as a function of magnetic field, this there is a chiral state on board. Chiral state as a function of magnetic field. Evolution. So suppose one keep the Fermi level at the middle, means mu is equal to 0, and do the measurement, thermal Hall effect measurement. So what should we expect? Means there are two chirales, so one should expect the quantization of the heat current in terms of that unit or something else.
It's not going to be quantized.
Yeah, but what I'm saying means suppose you keep your Fermi level at the middle, means at mu is equal to 0, and at mu is equal to 0, there are only the two chiral edge states, right?
You mean for the Y electron?
Yes.
For wire electron, yeah, there's some work on the understanding of this summer Hall transport. For this electron system, things are actually much simpler because of their Fermi levels. If you tune the Fermi level to be right at the nodes, you are only worried about the states near the Fermi level. So what contributed to the Hall transport are these edge states. You just count the number of edge states responsible for the Hall transport. For instance, for usual electron, for the usual Hall kind of measurement, not thermal Hall measurement, you just sum over these Y nodes contribution.
Okay.
Weighted by their chirality. You add some fundamental constant in front, will give you the whole response.
Yeah, so I was expecting that the part of these two states, just one is moving right, moving, and one is left moving. So the difference should be 0. So should I expect the 0 thermal conductance?
No, you need to average with the chirality.
Oh, okay.
Add the chirality in front, weighted by so the momentum should be weighted by the chirality.
Okay.
These nodes have different chirality.
Oh, yeah.